In this video, we're going to cover the topics of concavity and the second derivative test. We're going to start with concavity first by defining it, and we're going to break it into two parts. So the first part says, a graph is concave up when f prime of x is increasing. Okay, so let's think about what that means. In this context, f prime of x we often think of as the slope of the function. And so if the slope is, I said increasing, didn't I? Let's try that again. There we go. If the slope is increasing, that means it's becoming more and more positive. So what does this look like graphically? So the most common way we see concave up is with the upwards opening parabola. And we have this property described here because on the left side, as we go down to the right, these are negative slopes getting less negative till we reach a zero slope, and then the slopes continue to get more and more positive from there. So this is an example of concave up, and I'll use this abbreviation for that throughout today's video. And of course, the other one we're going to consider is when a graph is concave down, and that occurs when f prime of x is, of course, decreasing. Okay, so again, we're thinking the same thing. So this time, we're still thinking of the first derivative as the slope of this graph. And if it's decreasing, then the slope is getting more and more negative. Okay. So visually, we're thinking of it as kind of like an upside down bowl or cup. I like to think of cups since concavity with a C. Anyways, and the reason this works is because we start out with positive slopes as we move to the left. They become less positive, eventually zero, and then they become more and more negative. Okay? So this is an example of a concave down, or it's like a cup turned upside down type of function. And so today we're also going to be working, obviously, with the second derivative a lot. And so we can describe these things using the second derivative. So for instance, when we're talking about f prime increasing, this was like when we talked about velocity increasing, and that occurs when the acceleration is positive, or in a more general sense, this occurs when the second derivative is positive. Okay? And then similarly, if our slope is decreasing, that means the second derivative, or how the slope is changing, is negative. Okay? So this video is focusing on the second derivative. This is how we use the second derivative to identify when a graph is concave up versus concave down. We look for when it's positive versus negative. Okay? So the next kind of definition we have to go through here is what's called a point of inflection. Sorry, my pen really doesn't like eyes right now. Oh, there we go. Okay. Which we abbreviate POI in a lot of cases. And that is where the function changes concavity. Okay? And so this would occur wherever the second derivative is 0 or undefined. So that's a common thing we look for in this unit. Because that's where it's switching from either concave up to concave down. So the second derivative switches from positive to negative, or vice versa. So to do that, it has to either cross through 0 or be undefined. Okay, so that's a vocab word. So we had our critical points, and now we have our points of inflection. And they're two different things. We got to keep it straight. So let's do some quick pictures here to kind of think of some scenarios and just get a general sense. So the most common way we think of concavity is just kind of like, I guess it's a more obvious way, but and in this case, the point of inflection is where it's switching. So it's switching from an upside down cup, which would be concave down, to a cup that's opening up. And where it's changing is right here at the point of inflection. So that's our point of inflection for this graph. Okay, so it doesn't have to be a full cup shape for it to be concave up or concave down. So this is the easiest kind because it's almost a complete version of each type. Often they're not full cups, so to speak. So another one could look like this. Might be a little exaggerated there in the middle. But the first part of this graph is kind of like half of an upside down cup. So it starts out concave down, and then somewhere around here at this point of inflection, it switches to a right side up cup shape, or concave up. Okay. Another way you might see it looks kind of similar to this, but instead of going flat in the center, the kind where it's kind of a vertical S shape, and I'm not great at drawing these, so bear with me. So it's like if we had a more of a this type of curve. Okay, so again, it starts out kind of opening up, and then it switches here to concave down. Okay, so those are some basic examples you'll come across. Then there's the kinds that don't have any points of inflection, or just types of concavities that might not, again, be that whole entire shape we're used to seeing. So for instance, if you have a function like this that's always increasing, we can tell that this one is concave up, and it has no point of inflection, right? It's just staying concave up. Another way that might show up is going in a decreasing motion. Okay, so these are both examples of concave up with no inflection points, where it's not changing concavity. And then, of course, the same can be true for concave down. So sometimes we have something like this. And sometimes we have something like this. Okay, I guess it probably would have made sense to flip-flop these. Sorry, I get too OCD about this. So concave down, but increasing, would look like this. And then concave down, but decreasing, would look like that. There. That makes me happier. Okay, so here's how concave up can increase over the entire function, concave down, and then decrease and decrease. And these have no points of inflection. Okay. Okay, so now we're going to go through the steps of how to determine concavity algebraically. So your first step would be to find the second derivative. That's what we're focusing on here. Okay. Then you need to find where that second derivative is either 0 or undefined. And remember, it usually undefined isn't one we have to really worry about, but you always need to check. And then you're going to make a sign chart with those x values. Okay, and then of course, based on those signs, you're going to use those signs to determine if the function is concave up or concave down. And luckily it's intuitive. A positive answer means concave up. A negative answer means concave down. All right, so let's try an example. So this is actually the same function we used in the previous video for the first derivative test. So it maybe look familiar. So find the intervals on which f of x, nope, I'm going to put him, it's kind of a long equation, so on which f of x equals 4x cubed minus 15x squared minus 18x plus 7 is concave up and concave down. Determine all points of inflection. So points of inflection, just to kind of do a quick side note, they're a lot like relative extrema, where we'll get potential x values that might be points of inflection, but if the concavity doesn't actually change sign, just because it's an x value that makes the second derivative 0 or undefined doesn't guarantee it's a point of inflection. So we got to check using our sign chart for that. All right, so let's do our first step, which is to find our second derivative. So let's find the first derivative. So that would be 12x squared minus 30x minus 18. Then we can find the second derivative, which would be 24x minus 30. Okay, and so we're going to set it equal to 0. So that's going to be 0 equals 24x minus 30. And then we're going to solve. Sorry, my dad talks on the phone really loud, apparently. I'll see if I can do something about that. But first, let's go ahead and solve this. 5/4 equals x. Okay, and then we look at the potential for it to be undefined. And of course, since this one's a polynomial, that's not really an issue for us. All right, so it looks like we have 1 point for our number line. Okay, so we're only testing 5/4, and we're just kind of substituting it back into this second derivative, 24x minus 30. So obviously anything to the left of that will simply be negative, and anything to the right will be a positive. And remember, this represents our second derivative values, and then we're going to talk about what that would look like on our function. And so if it's a negative second derivative, then it's going to open down, concave down, and if it's positive, it's going to open concave up. Now when we get to curve sketching at the end of this unit, this is just a general idea of what's going on. Obviously, we don't know if it's making this whole shape, or again, like our previous examples, if it's just like the left half or the right half. More information is needed for that. But this is just like a quick way to visually start thinking about what's happening on the graph. Okay, so let's write our answers the way you're expected to write them with your justifications. So this would mean that f of x is concave up over the interval 5/4, comma, infinity, since the second derivative is greater than 0 at that area. Okay, and similarly, the function is concave down over negative infinity, comma, 5/4, since f double prime is less than 0 on that interval. And lastly, as far as points of inflection, we only had one possibility, right? This is a possible point of inflection. Then when we look at the sign chart and we verify that it changes signs, we can state that it is a point of inflection. So f of x has a point of inflection at x equals 5/4. Sometimes they'll want you to write a coordinate point here. Obviously, if that were the case, you would just take this and plug it into that original equation again, but I'm not going to make you do that right now. And the reasoning is since the second derivative changes sign at that x value. Alright, so this brings us to the actual second derivative test. And just like the first derivative test, the second derivative test is really telling us where our relative extrema are. So where are the max and min located? So we can use the second derivative to understand concavity, which is how it's most commonly used. But this second derivative test is just a way to verify where those maximum and minimums are, and is not so much focused on the concavity necessarily. Actually, that's not true. It tells us the concavity, which tells us if there's a max or a min. Okay, so let's go ahead and define it. So let f be a function such that, and remember, we were talking about a c value, like some special x value, so such that f prime of c equals 0 with the first derivative. And it's not 0 or undefined in this case, it is specifically that it equals 0. And the second derivative exists on an open interval containing that x value. Okay, so that's kind of like the part that has to happen before we can even do anything with the second derivative. Okay, and if that's the case, then if the second derivative at that value is positive, we know it has a relative minimum at that point. Okay, and visually think about why that's the case, right? So if the second derivative is positive, then this means we have a concave up section of the graph, and thus anything with a slope of 0 would occur at a minimum, a relative minimum. Okay, similarly, if the second derivative at that critical point is negative, then the function has a relative maximum at that point, right? Because if the second derivative is negative, that means that our function has a concave down graph, and thus any slope of 0 would be occurring at a relative max. Okay, so that's how we're using whether the second derivative is positive or negative to determine where the maximum and minimums are occurring on our graph. If somehow you get the second derivative at that point to equal 0, then the test doesn't help you. Okay, it means a lot of things. Usually it means that there's not a relative max or min there, but sometimes it just means that the second derivative test won't help you figure that out, because that's not always the case. So we just say then the test fails. So you would want to just stick with your first derivative test we did last video to determine that. So if all this does is what we already know how to find from the first derivative, what's the point? Well, it's kind of like a backup test. A lot of times you can use it to check your work, and it does the same thing as the first derivative as far as telling us where the relative extrema are. So like the first derivative test, it tells us the relative extrema for a function. That's the point of it. Okay. Why do I need to know it? Sometimes it is useful when we can't create our sign chart. So, useful given certain information. So, one way you might possibly see it, let's do a quick example here. Let's say we have a continuous function, and at x equals 2, we know f prime of 2 is 0, so it's a critical point, and the second derivative at 2 is negative 3. So what's going on there? Well, with just that information, I can't create a sign chart to see if it's a maximum or minimum using the first derivative only. So this information alone is enough to then confirm that we would actually have a relative max. Okay? So that tells us there's a relative max using the second derivative test, and it's very quick in that case. But like I said, most of the time I don't actually use this test unless asked about, or in that special case we just looked at. But let's see how it would work. So we're going to do one last example here. Okay, so find the relative extrema for the function f of x equals negative 3x to the 5th plus 5x cubed using the second derivative test. Okay, so let's find the derivative first. So the first derivative would be negative 15x to the 4th plus 15x squared. So we're still going to do like we do in the first derivative test. and find these critical points for this first derivative, but we're looking specifically at the ones when the derivative is 0, not undefined. So I'm going to go ahead, let's factor this a little bit first. So I'm going to factor out a negative 15x squared times x squared minus 1, and of course we can factor that one more step. Difference of squares to x plus 1, x minus 1. Okay, and I'm actually, let me just kind of skip a step here, set it equal to 0. Okay, so I'm looking for when that first derivative is 0, and that would occur in this case at x equals 0, negative 1, and positive 1. Okay, so now we're going to find the second derivative. Okay, I'd just go back to this original form for that, and we're going to get negative 60x cubed plus 30x. And I'm going to go ahead and factor that as well, if possible. It should be, so negative 30x, 2x squared minus 1. Alright, good enough. So now we're going to make our little sign chart. But this one's more like the one we do for the absolute. I'm going to actually use green here. For the absolute extrema, where we use x, and then in this case we're going to evaluate it in the second derivative. So the x values we're checking are negative 1, 0, and 1. We got that from where the first derivative is 0, because those are the potential points for us to have relative extrema in the first place. And now, instead of doing like our traditional sign chart with the pluses and minuses, I'm just going to plug them into this function here. And I only care if it's positive or negative. You can actually evaluate it if you'd like to. So I'm going to plug them in and get a number, but I really just care about if it's positive or negative. So if I plug a negative 1 in here, you can already see it's going to give you a positive here, and then another positive here. So it's going to give you a positive second derivative. The actual value is 30. Not super important, but there it is. 0 is pretty easy. It's just going to be 0 times something else, so it doesn't matter. That's just going to be 0. And then a positive 1 is going to give us a negative times something positive, which would be a negative value, and in this case happens to be negative 30. Okay, so based on that, let's determine the concavity, right? So this is positive, so that means it's going to open up. And this one's negative, so it's going to open down. And if you remember, when we get 0, that's something we can't determine using this test. So does it have a max or min? Well, if it opens up, that means we have a minimum. If it opens down, that means we have a maximum. So let's write our conclusion. So there is a relative minimum at x equals negative 1, since f prime of x equals 0, and f double prime of x is greater than 0. And then there is a relative max at x equals 1, since f prime of x equals 0, and the second derivative is negative. And that is all there is to the second derivative test.